Okay folks, welcome. My name is Eric Wooldridge. I'm Associate Professor here at SCC, and my specialty is pre-engineering and additive manufacturing. Today we're going to walk you through some of the new technology that's recently coming down the pipeline, and then explore some of the things we're doing here at SCC. So, without further ado, what we're focusing on today is first of all, the state of affairs for additive manufacturing. Now, everyone calls it 3D printing. We use that term back and forth all the time. But additive essentially means that we're just building something up. So real quickly, one of the things that's happened, you've seen it in the news, you've seen articles, you hear about children getting new legs and hands and all this really, really cool stuff. But one of the things that we've been waiting on is, when does it become something less of a novelty and more of a common practice, a common production? For example, the chairs and the tables and things that you're sitting in are conventionally produced. Someone's actually putting those parts together. And the question was, when does additive become to the point where it's being used to make those parts that you are the end user receiving? So, what we anticipated happening was a longer while down the road we would start to see that happening. But what's happened is we're starting to see it happen now. We're starting to see a shift from 3D printing, from novelty, prototyping, special custom stuff, to 3D printing production on a larger scale. So it's happening sooner than we anticipated. This was the intentional barrier. What we thought was going to happen was essentially conventional manufacturing was going to stay ahead because of the cost issue. Conventional manufacturing gets less pricey as you do more volume, which is mass production. Everyone understands that. And the only time that additive had sort of its point and its happy zone was in smaller runs and more complexity. So as we became more and more complex, more and more elaborate in design, we actually could use additive, but once parts went into high volume, then we weren't going to use additive effectively. That was the perceived barrier. However, what we're actually starting to see, especially over the last 6 months, are articles like this. Companies are switching over to production. So we're starting to see the actual change from prototyping to production happening much, much sooner. For example, we see that Oracle has used a new system, Carbon 3D, to actually start creating parts for some of their electronics. So there's no one actually conventionally making this part, that's all being 3D printed. And we're talking large amounts of them, 10,000 unit runs. We're also seeing a lot of articles like this. People from around the world and leaders are starting to say, we want to switch and everybody wants to be the leader of this new digital manufacturing age. And Carbon's also in the news in the fact that they get to mass produce some molecular models for education purposes. Then we get a story like this. This boy has a size 28 foot, gigantic foot. He's like 7'9" or something like that, 19 years old, just huge shoe. And now there is a company that specializes in printing shoes. So, and not just sizes for him, but for anybody. It's called feets.com, and they actually have these little printers that actually print in the same materials that you would typically have, actually custom-made footwear. In fact, actually all you have to do is send pictures of your foot to them through their little app, and they can actually model the feet. So he actually gets to have shoes that he never had before because of this company. And the price difference is, negligible. Normally custom work for something like that was huge. Now it's the same as ordering a size 10 or a size 12 for this particular company. Now, since they did it, we see that Adidas is now looking to partner with a particular fast printing company. Their particular system just really runs really, really fast, and start printing shoes. And you can see you can actually check out their YouTube video on it, but they're actually printing the soles of custom footwear. So they're switching to a concept of mass production of printed soles. Now, we're starting to see this a lot in the aerospace. So this particular aerospace system says they are cutting costs for a particular line of part by 30% by switching to serial production with 3D printing. Now, keep in mind the part itself is actually fairly simple. It's this little bracket that you see right here, or actually just a little cover. It's plastic, it's small, but it's printable. It's not being plastic injection molded, which is a big deal, because normally that's where plastic injection molding at its bread and butter. This is actually a part that is printed on demand. Then we see others. Boeing applies for a patent to actually patent the process of printing parts for aircraft. Now they actually mention in the article that it's for repair work. It's for replacing parts that are no longer typically made, and having a digital database of files so that when maintenance operations needs new parts, they can actually just download and start printing the replacement parts for the aircraft. So it's not truly production, but it's a big step in that direction. They're starting to tread into those waters. Then we have Airbus, who says now we have finished testing this new part that we have printed out of metal, and it's a very complex part. It's actually been field tested, and they're switching to actually printing this and being in the aircraft. And this isn't a plastic part. This is a part that is going to affect the functionality of this aircraft in the air. So obviously they have crossed their T's and dotted their I's a lot to this point, but they had a lot of interesting data about it. So you see the part down there, and specifically they have a little bit of data that they say that by switching to printing this part instead of conventionally making it, they have reduced the weight by 60% of this particular part, and they've compressed it down 30% from the size it used to take up. So this particular actuator, which is controlling some of the hydraulics for the aircraft, is actually lighter weight and smaller, and increased reliability and decreased cost. So they've saved money, they've improved performance on several factors, and they've improved the life of the part. And it's going to be in their planes. Then we have an article like this. This is about a company called Electrolux acquiring a Louisville-based company, Grindmaster and Sisselwell. Excuse me. Why this is important is because the day that this article came out, we saw another article, a separate one, that pointed out that Electrolux had just made a deal with a Chinese printing company to actually have a database of all their spare parts. So this company was in our local news because they were buying out some folks in our area or in our state. But at the same time, the head company was making deals with Chinese companies to start printing their parts for repair and work. Then you've got this company called Man Diesel, and they actually create turbo engines and those kind of things, and they're just going ahead and saying that they are switching to printed part production versus conventional manufacturing for certain parts. And then why not? You've got the U.S. Army that actually recently published an article where they actually fully printed a grenade launcher. And now they weren't planning on switching this to production. This was just a test to see if they could do it. But you will notice one particular aspect of the grenade launcher that is different than most weapon systems. If you look at the grip, you see that the grip is actually a little bit more hollow. They did this because they could. With additive manufacturing, we can make a grip that's lighter weight, but still functions the same. And it was sort of a treading the water kind of thing on the Army side. Then we have an excavator, your typical little miniaturized track hoe here, that has multiple printed parts on it. I'll show you. First off, the bucket was printed in metal. The boom component right here, printed in metal. And in fact, if you look carefully, you can see that this little tunnel where the hydraulic fluid is transported is actually printed in the design. So it's not a separate loop or connection point. Hydraulic fluid is actually going in through the part itself. And also printed, if you notice the kind of elaborate little detailing right here, the roll cage was printed. And you can't see it, but a heat exchanger on the inside of the equipment was actually printed in metal as well. So it actually had several components that were printed, and you can see this thing operating down in Tennessee. They took it to Vegas as a demonstration, but you can actually see it operating. It's just handling the stress. It's really, really neat part that we got to check out. Then, while you're at it, and you've got your monster truck, might as well print a wheel for it and a jack. You know, why? Why not? And in all honesty, why not? Because someone just decided they wanted to show off how additive manufacturing can produce workable things, so they made a wheel and a jack to go with it, to hold the truck up. So, I don't advise getting a monster truck just to demonstrate that, but you know, whatever works out for you. So the question started to be posed, why are these companies switching? Is it to save cost? Because that's true, they do save cost. Is it to save time? Well, that is also true, it is to save time. And supply chain reliability, basically reducing the number of vendors and printing it yourself, is helping them. And it's also sustainability. The sustainability side is we're having less involvement with materials that we don't know where it's coming from. We don't know the labor that was used to get them there. We are getting benefits there, but that's actually not the primary reason that we're seeing. The primary reason is performance and complexity. What I mean by that is if you look on the screen, you'll see these are heat exchangers. And notice, first of all, how complex this design is. Look at all the curves, all those features. Look at this one. It's got all kinds of things that you normally don't, and this is basically a giant radiator if you just think of it that way. In terms of heat exchangers, they're just big radiators. But you look at these designs and they're incredibly complex and organic. But, and even these, more organic, natured, complex, this one the same story. But the reason that they're taking the time to design these elaborate things is because they're getting higher performance out of the product. Not just a small amount, a significant amount, enough for them to realize, hey, we want a new solution and we don't care so much about whether or not we can make it because we know we can. Specifically, go a little bit further with that. GE announces not too long ago that they're buying out a couple of metal printing companies, specifically a Concept Laser and one other. They spent probably about $1 billion in the deal. And then they announce they're going to turn around and put another maybe like $500 million into Expanded. So the question is, why is GE buying out metal printing companies, and why are they pumping more money into those companies to do more metal printing? And here's what they tell us. This was a recent presentation we received. This is a fuel nozzle. This actually was developed several years ago as a test run, and it's actually being used in their turbine engines. So if you're on a plane with a GE product or GE turbine system over the last couple of years, in terms of it's a new model, it's got these new parts on it. They went from trying it out to producing around 35 to 40,000 of these a year, or that's their overall target goal. They're scaling up to do that. Here's what they said. By switching to printing this part, they had 25% weight reduction. It's a small part, but that's still significant. They are 5 times more durable. That's a big deal in aeronautics. Then, here's the big kicker. This part used to be composed of 20 pieces. Now it's 1 part. So no longer is someone assembling this part. No longer are they having 20 different pieces coming together to form this part. When this part is done printing, it is ready to go. Now you can't tell in the design from the outside, but what's happening on the inside are tiny little channels going all kinds of different directions that are virtually impossible to manufacture conventionally, but can be printed without a blink. That's the kind of concept we're looking at here. So we can print so much easier, get better results out of it, and it's almost a no-brainer for them. So they started off with this particular project, and here's some of the data they received from it. First of all, here's all of their savings. No longer, the green is the new part. No longer do we have to worry about inventory, because we don't have to store parts. We print on demand. Look at the life cycle cost. Here's the comparison of the old nozzle, here's the new one. Overall, in terms of its life cycle, from the point in time it's created to the point in time it disappears wherever or is recycled, this is how much cost is embedded in it. Manufacturing cost, they had a reduction. It's not as dramatic as this one for sure, but it's still lower cost. Then we have the part weight. So all of these benefits are parts of the process. Also, in terms of, although not really pointed out here, when you go from having 20 parts to 1, it means you no longer have other manufacturers involved in the process, which means you no longer have staff coordinating that process too. Then they gave some more information. What their kind of realization was with that, additive manufacturing allows us to do things that no one else could prior to this. So since we're after complexity, we want to try more. So here is another test example. What they did was this is a turbine system. So GE looked at a comparison between the old way of doing things and doing with additive. Here are some of the results. In this particular part, this design right here, conventionally, it used to be composed of 300 parts. It took a team of 60 engineers to kind of get to this point of production. Now, 300 parts gets reduced to one part. We went from 60 engineers to 6 to 8 engineers. Think about right off the bat the economic impact of reducing that workforce and also reducing that production. 300 parts were being made for products like this, now one's being made. That's a lot of jobs. Then, in terms of actually getting those 300 parts made, it took 50 plus manufacturing resources, or sources. Now, we condense it down into one unit. It took 40 data systems of coordination and processing and all these things to make it happen. Now, we're down to one data source. It had 5 different places associated with repair or replacement or different locations that had to contribute. Now we have one. So this one part that they've switched to additively printing in metal has reduced a significant amount of the workforce, the inventory costs, and everything. So GE's looking at this data and it's unquestionably different from everything they've ever done. So, as a result, they're trying out new options. This is the new turbine engine. They are basically what goes on Blackhawks. Here's what they had as a result. They went from a 12-month testing schedule to a 6-month testing schedule. They got it out that much faster. They had a 5% weight reduction. They went from, and this is pretty significant associated with their particular work, it has a 20% lower emission fuel burn, which means essentially, that's huge in terms of aeronautics. So they've had increased performance, they've reduced the weight, they've increased their production time and testing time, but here's the kicker. They went from 855 parts to 12 for this assembly. That is a lot of jobs that are no longer going to be necessary. In fact, they even commented that one of the major American casting companies that participate in usually GE's production of equipment like this, they hear they're working on a new engine, they call it the CEO, and they said, when we're going to get some drawings so we can start making some casts for you. And the CEO said, I'm sorry, we won't need your services this time. That's a big hit. And why is GE doing it? Because they can get better design. They can design for the solution instead of design for can we make it. Now, they also pointed out this data on that process, and just to kind of quantify it very quickly, this is the traditional way they did things. They had a lot of design time built in and a lot of build time just to get the prototype out the door. Now, here's our design time. Here is our prototype. This little bit of red that you see right there is the prototyping and building time. Then we've suddenly got plenty of time to do some testing, redesign, rebuild, test again, redesign, rebuild, optimize it after that point, and then build it again to actually get into production. All while conventionally, all this time was the first prototype build. Huge, huge time savings, and the design's better because we were able to redesign it 3 or 4 times prior to ever getting to production. There's no optimizing time here. This was just the first build. This build had optimization built into it. So by the time the product hits the market, or is actually ready for its first market release, it's already gone through multiple stages of redesign and tweaking. A big deal, obviously. So, here's what GE's doing. They bought these companies that print metal, and here's what their anticipated results are. Just on the metal printing side, or the GE additive side they call it, they anticipate $1 billion annual revenues by 2020 on their metal printing side. They plan on shipping out 10,000 units of these metal printers by 2026. That's in addition to the metal printers they're using for themselves, and they plan to cost out $3 to $5 billion by 2026. So they have decided they're going to be the leaders in metal production printers and metal production productivity. And they're going to sell it to the competitors. They're going to get as many metal printers out there. In fact, they're even offering grants to schools and colleges to get into metal printing and FDM in that case. So, this is a quote from one of the GE leaders and one of the teams on their additive side. He said, you are either going to be a leader in this technology or you will be a victim. It's his call to all these companies that are just staying with conventional. Take a look at Caterpillar, a company that's not aerospace, a company that we know for heavy machinery. Look at what they did. They started off with trying to fix a problem. They switched over to saying, hey, maybe we've got this ball valve that always gives us problems, it leaks, it makes noise. What can we do about it? Well, somebody said, let's look at printing it. And they tried a redesign by printing it, and they reduced the part count from 5 to 1. Hopefully by now you're seeing that part count reduction is a big thing with this process. They reduced the cost by 55%. They had a 33% pressure drop problem taken care of. They basically made the system more efficient, and they even got a benefit of making the noise reductions go away. Or they basically made the noise go away, so they fixed their leak, they got a better part, they got a cheaper part, and they actually made a more efficient part in the process. So that first step was a step in the right direction, so they went to another one. Caterpillar also owns a company called Solar Turbines, and this is a turbine system. And essentially they were conventionally making this part. Use the wrong tool there, hang on. They made this part, and they were running into problems. So they decided to start printing a different version of the part, a part that was more complex that they couldn't make conventionally, but they could with additive, and they received good benefits out of that. I think their data was very positive. These were called fuel swirlers. And they actually printed out 500 plus by 15 and actually started implementing them as production. So they looked at a bunch of different applications. Every single time we're seeing things like cost reduction, improved time, and the more they do it, the better things get. So then someone has this idea at Caterpillar, one of the CEOs I believe. He says, you know what, we've had this engine, and we have to overhaul this engine at 8,000 hours. Someone has to go in and do a serious overhauling. And they have tried to increase that 8,000 hours conventionally, making new parts and trying stuff, and they've never been able to make dramatic increases. So they even say minor improvements have been tried with conventional and no sight to the life goal. They want to take this thing from an 8,000 hour overhaul to 20,000 hours. They don't want this thing to be overhauled for a factor of 2.5. They want to extend its lifespan, essentially with this. So the CEO comes to the design team and he says, you know what? Let's change our approach. He said, now I want you to design a solution for this that's going to get our engine from 8,000 hours to 20,000 hours. He said, I want you to design it so that you're not concerned with whether or not you can make the parts. Just design it to solve the problem. Whatever crazy concept you come up with, just design it and let's see what happens. With this design challenge, they had 45 ideas, 45 different submissions. They're actually in testing of 3 of them right now, and they're pretty confident they're about to hit their goal. So by switching to additive, they're now going to be able to design solutions that actually solve the problem, probably create lower cost parts, and take their engine from 8,000 hours to 20,000 hours. Think about the marketability they're going to be able to sell this engine for. This thing has now a lifespan increase of 2.5. That's crazy. They could charge about whatever they wanted to for that engine and be okay, because it's such a dramatic change, all because they're no longer concerned with whether or not they can make the parts. They assume they can, because additive can. So they're going testing right now. We actually asked them, what's the part design? They wouldn't tell us at that point in time, but it's coming out in the next run. So they are in the validation process, or expect to be into it soon, and to actually have a longer lasting engine. So Caterpillar, just like GE and just like all these other companies, have been in this test phase where they've been trying stuff out, and they've realized, you know what, there's some serious change happening here, and there's some serious potential. So it is all about the complexity. If I can design a solution and not concern myself with I can make it, that's all that matters. And so therefore, they're switching to additive to actually make that happen. So, what's SEC doing? Our objective is to do a broad spectrum approach where we create a certificate for folks to take. They can take it with any program that they're in and actually get a certificate in additive manufacturing, 3D printing. It's actually included with their digital literacy if they want to take it that way. But we realize with all of this push to design complex and solve the problem, don't worry about it if you can build it. We want to make sure that everyone has that skill set. So we actually have created a certificate, but then we realized to actually help introduce the process, we needed to produce more things. So we have modified our original grant to include 2 new lab technician positions. And the lab technicians are essentially going to help make projects happen for faculty and staff, even student work here on campus. So that's kind of our goal, to get an opportunity to do projects with you all that actually have an impact. What we're looking for are projects that are educationally based, solve a problem, help a person out, something that has an impact that we can report about, we can talk about, and then we can publicize and we can collect data on. You know, this was a problem, here was the solution, we 3D printed the solution, and here's how the solution impacted downstream. That's what we're after. Because at the end of the day, we're doing something that no other college in our region, and technically as far as we know in our state, is looking at. We're looking at the rural applications of additive manufacturing and broad spectrum, using additive to touch all kinds of fields. Production, manufacturing for sure, but also things like healthcare, marketing. We're looking at educational models, you know, how can we teach students better with 3D printing? And we all know that with this process, with AM involved, we can save money, but also we can increase awareness, increase notoriety for what we do, and of course increase enrollment with this. We want to be the leaders in the process. So, questions you all want to ask before we introduce you to some of the folks and get started with the lab production? Good.
Okay, as a teacher, I want to teach a teamwork class. That's what we already offer, small group communication. As a teacher, can one of my team projects be to divide the class into the smaller groups and challenge each one to develop something that would help within their industry? And can we come in here and use this lab for that particular teamwork challenge for another class?
Absolutely. That is literally what the positions have been created for. So you don't have, because who knows what I'm teaching or where I am sometimes, and that was our big problem, is that I was always the point man to getting something done, and I just don't have as much time as I used to. So we created the positions to be a lab technician who's able to run the equipment and assist whether I'm here or not. So absolutely, that is exactly what we wanted to do. We want, especially since it's a broad spectrum and you're trying to impact multiple different industries. Yeah. Other questions you want to ask? Yes.
So everything you said sounds good, except for the fact that it kind of makes you feel like the unemployment rate may go up because it is taking people's jobs. So
that is the double edge of it for sure. So, and we've been noticing that for a while. We know what actually happens when this scenario happens. So one of the reasons I'm even talking about it is to make the knowledge get out there soon so that companies can adapt. Because what we anticipate happening is that GE and Caterpillar and Boeing and all these other companies are eventually going to start seeing more and more opportunities, but they're not going to be able to produce all the stuff they want to produce. Like, their engineers are going to come up with crazy cool solutions to solve their problems, but they're not going to be able to do it in-house. They're going to start wanting subcontracting manufacturing, for example. They're going to want some of these conventional machine tool and operators to switch over to produce their parts for them. Still, they still want parts, but they want them produced additively because conventionally can't do it. So what's going to happen is, kind of like the casting company, they're going to say, you know, we don't need you, but we do need these parts, perhaps. Can you print them for me? And we're seeing the ASTMs coming up with standards for that process, because once we have this unified standard that says, hey, this part A has been produced by ASTM blah, 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 I can trust anybody across the nation to print it for me, as long as they say we meet these standards. The same way we do it now. So it's just a new process. So it's actually, what we're hoping to make people realize is, it's an opportunity for a whole new industry. But yes, we do see there's no doubt, the data already shows there's a cut in conventional manufacturing as a result of this. We're just trying to make people aware of it. But there's all kinds of great opportunities too. But yeah, it's a very real thing. Yes, sir.
So, you said that metal printing is available now, and I assume this means non-ferrous, or is it possible to print in steel also?
Everything. What essentially they're doing is just taking your typical metals and grinding them into powder. Okay, so we have aluminum printing, we have titanium, we have steel, stainless steel, everything. And take that powder and then shoot it with a laser, high energy laser essentially, and basically melt that powder at that point, and then move that laser. So it's all the same materials.
At some point it's liquefied?
Yes, essentially it's fused at that point. And the same way that our systems run and lay out one layer at a time, it's creating a fused layer one shot at a time.
And don't you run into corrosion problems?
You do. So what specifically GE is doing is they're pointing out there needs to be you have to have people that know what they're doing to make these parts work. So what they've actually come up with is their own internal standards for all their metal printing. So for example, the powder itself is never supposed to be exposed to air. You have contained process for reuse and everything, and they reprocess and recycle it. So as long as a person accounts for all that, they're getting these exquisite parts, for sure.
So it has to be completely shielded.
It does have to be completely shielded, and it's vaporized metal. So I mean, you have a lot of health issues there too. So you have to have proper ventilation, protection, and everything. That's why the equipment typically is more expensive in the metal side printing. Right now, you're probably looking at $500,000 for the equipment. But we're also seeing the movement. It's getting easier and easier to make because the patents have all expired. So you're likely to see it down into the 250 and the 100 zone. But the safety factors still always have to be there. In fact, there's actually two metal printing processes. Well, two basic ones. You get your powder form, and then you've got this whole other concept where they're actually, if you imagine like a MIG welder, just welding along, running a wire out, that can be converted into metal. Actually, the Excavator that you saw was a metal wire printer. And so that's really just a MIG welder attached to a robotic arm following the path. In fact, one of our, we've got 6 robotic welders over on South Campus, and we're looking at converting one over to start doing some demonstration printing processes. So that's even safer. It's actually equipment we already have. It doesn't have so much. You don't get as precision work with that, but they demonstrated they can actually print excavator parts with it. So it's a different ball game, but it definitely has serious potentials. And we'll probably see some over. Yep.
I have another question for you. Since I am a shepherd and a farmer and deal in wool, how can we use wool using additive manufacturing? For example, I know that felting is used for the overhead liner and the flooring in automobiles, as well as another process that adds to that fabric for the fender covers, that type of thing. And so what would be the future of other resources besides metals that can be printed?
Well, first off, there's always an additive application for something. Even what we're actually seeing is you can actually improve whatever process you normally do for even raising animals. There's probably things you could be printing with FDM things that just help your process. We've seen everything from gate latches to actually little features to help in the grooming process. But as far as the commercialization of the wool, what we are seeing is a significant interest in the fashion industry for starting to find ways to print clothing. In fact, there's actually some clothing printers out there. That one is a tougher one to do, but it's already being done. I mean, we've already seen a t-shirt printer made successfully. So the answer is it's coming. There is a desire to do with additive in that realm just the same as they're doing with metal and everything else. Right now, the market's probably there. People are wanting to have custom all the time, but the machines aren't there yet. But I actually, the Google exec recently said he anticipates clothes printing within less than 10 years.
Well, that would help with our hemp industry if we can get that going in Kentucky, because that is another really tough fiber.
Absolutely.
Really tough fiber. And wool and hemp together, if treated properly, are as strong as steel.
Absolutely. And that's what we're seeing now since, we'll talk about this when we look at these machines are working, and they do a really good job. So now people are coming up with all kinds of different materials. And we're seeing that. So like the metal side, they started off with like steel, but then immediately aluminum and titanium, and there's a bunch of companies that are just getting into the metal powder production industry just to have material base to support all the printing applications out there. Same thing's going to happen with, on the wool and the hemp and everything else. Somebody's going to come up with a platform that makes it work. Then they're just going to need materials. And so then there's going to be the push to supply the materials, because you're cutting out so many handoffs. You're cutting out supply chain problems that typically we have with production. And it's a miracle, in all honesty, that we make things in general, considering how many places across the world parts have to come from, and how many different suppliers, and how much different import-export issues we have. So when we suddenly just get the materials and have a platform to put them in, and we don't have any more of this problem in the middle, your supply chain can be just very rampant. The negative side is it does lend itself less toward mass production and custom production. So your waste and your inventory needs are just going to reduce, and so therefore the demand for material may not be as great, but there's going to be a demand for the better materials, for sure. Yes?
What about in the healthcare industry?
I'm glad you asked that question. So, healthcare industry was already on board because of the customized nature of the healthcare industry. So we've demonstrated we can produce MRIs. We can actually print off body parts for diagnostics, for surgical prep. We can print them off in soft materials. But spinal implants have already been done. Quite a few of them have already been done. There's already been skull implants that were printed. Shoulder, knee joints have already been printed. There's actually some heart cell patches that have been printed recently. There is a bone structure printer that have successfully, they've also printed actually blood cells, like blood vessels themselves. So that research is huge. It is. And the FDA has already approved several applications. In fact, we've got FDA approved plastic we just got in the mail today, just for some food prep applications. So the FDA is already approving several additive processes for surgical implants, and it just keeps growing. We just see more and more. Heart patches specifically are really interesting.
So have you seen any in like actually a heart? Like if you need a heart transplant,
Yeah.
really all you need is like a model to go by, right?
Yes, in theory. So one of the first ones that I saw was actually some skin cells, where some printable. They weren't actually necessarily human. They was actually more like a fabric, but it responded like a muscle cell. So that was the first concept. What the biomedical side typically does, it's all about. They've actually switched to growing things. For example, there's companies that are actually growing your liver. They're experimenting with that. But what they found is the key thing with the printing is it's all about the structure to give the cell something to grow around. But yes, the heart application is one of the big ones. So like the patching will probably happen first.
Right.
The patch cells that they're actually able to put in and repair damaged zones, the blood vessels. But there's no doubt there is a lot of research going toward doing the whole thing. The livers are pretty. They've actually successfully done the livers, and the kidneys are probably their starting points. Yeah. They did it initially for the process of doing FDA testing, drug testing, without having to have a human person. They can just essentially print the organ they want to test on, and then avoid all that complication. That was their mentality. But then they were successful, and they got a lot of people thinking in that direction. But yeah, there is a lot on the medical side. Implants right now are probably your first thing, the ability to create customized, perfectly designed implants that aren't conventionally cut out material, but are actually modeled and shaped per the person's MRI, that just go right in. And those were the easiest to approve, so to speak. And they're typically metal titaniums. But your growth of cells was your next step. This is where we start to see the bone printers and the other cell printers. So a huge amount in the medical side.
The heart patch, what was it made of?
It's basically, and I didn't read the article fully to understand exactly all the science of it, but they had come up with a process to basically print heart cells in a structure that can be applied and to the damaged areas of the heart.
Was it like fabric?
I think it was actually a small amount of cells, so I guess it wasn't a fabric, but it was actually like a structure on there. It's actually a recent article. I can show you where it is. Yeah, it was pretty amazing. Yeah. Now, the other side of this is also just the typical usage. For example, casts. We can print casts all day long. We can actually print the casts that have little points where you can add like nodes to stimulate the growth right there. It can actually potentially heal about 30% faster. And we can print those casts that you can actually take showers in. They're actually exposed, so you can see the area that you need to. You only have to print what you need. We saw actually at the presentation, they saw one of their managers had actually had wrist surgery, So they printed him a support to hold his wrist in place, got rid of the whole cast, and it's actually just a very small piece. It actually just strapped on right here and held it right here and left all this exposed so it can be kind of checked out very easily. You can shower and everything.
If you've ever had a cast, you'd appreciate that, the
Absolutely.
itching and.
Yeah. Get right into scratch it all because it's very actually open and porous because there's only material where you need to hold the stress. So the medical side, absolutely. And I even consider the orthopedics, you know, the feet, the shoes and stuff like that. I mean, that's medical applications already. And not just Adidas, but Under Armour and Nike have also are making deals to actually do a 3D printed shoe line. So shoes are probably the first. Yep.
What kind of a footprint does additive manufacturing leave?
That's a very good question, and it often depends on the material. Now, the metal footprint, obviously, you don't have shipping, you don't have employees, you don't have to have inventory, so there's a lot of overhead sustainability issues that are no longer there. And you saw on the life cycle cost of that fuel nozzle that there was a significant decrease just in that fuel nozzle. So, but then you consider like some of the materials we can use actually could be fully biodegradable. So we actually did a project with a particular company where we helped them develop some processes for printing components that were involved in fracking so that the parts would actually dissolve within a matter of months after being used.
Is that what the new K-cups are supposed to be like?
It's hard to say. I don't really know. In that particular application, they came to us just to say, we've got this material, we want to use it, we can't use it in plastic injection molding. Can you help us figure out how to print it? And that's what we did. So I don't really know. I just know that it goes away fast. And there's actually some seaweed printing material you can get too. So there's no doubt, I can't quantify it, but I can say the additive footprint can be greatly reduced. Life cycle, carbon, everything. Significant. Anything else? All right, so let's have a little tour. Kay seems like really excited to talk about what she does.